like to thank everybody for coming today, and the subject of the talk is advances in high throughput microscopy. We live in exciting times. The technological revolution continues unabated, and we have tools at our disposal that allow really remarkable performance levels to be achieved, far more than in the past, and they show no sign of slowing down. So let's get started. I should probably begin by pointing out what, at least for us, high throughput microscopy is not. It's not super resolution microscopy. That frequently involves sparse objects and is computationally intensive and is slow. We're talking about high throughput microscopy at the highest levels. It's also not based upon a COTS microscope. And by COTS, that's an FLA, or four-letter abbreviation for commercial off-the-shelf. These are almost invariably bespoke instruments that are designed for a very particular application. It's not targeted at individual researchers. We are not supporting individual academics. A lot of effort goes into configuring a system of the types we're going to be looking at, and generally speaking, that effort is only justifiable, at least in our business model, when the customer is planning on making a number of these, and so this is targeted at OEMs. And it's also not sparse targets. It's as dense as you can pack the objects in there, and we aim to get you as many of them as quickly as possible. So we're talking about large area fields of view, high numerical apertures, high target densities, doing so in a way that is diffraction limited. Now, it might be fluorescence, it might also be bright field, doesn't matter really, but it is typically optimized for a particular application. We aim to give you what you need and no more and no less. As I mentioned, targeted at OEM instrument makers, and there's a few of the typical application fields that are there. And we keep hearing new ones pop up every day. It's really pretty exciting. So on a quick comparison of a COTS microscope on the left, stylish, heavy, expensive, and most importantly, general purpose. It's never going to excel at any one thing, and it's going to be too heavy and too expensive. So we're really talking about bespoke designs. Now, they may in fact just be a Lego block collection of some of the advanced tools that we've managed to put together, but they will be for a particular purpose. And the two systems on the right are both 3-axis, 3-channel fluorescence microscopes that had as their primary design goal that they had to fit in a ridiculously small space. So they're each about the size of the scientific CMOS camera over here. But you know, we do other ones that are larger, but the point is, if you have to make it small, we're good at small. Now, we'll be talking about 3 core functions today. Those are precision motion, optics, and sensors and cameras. They don't stand alone. If you're going to make a microscope, you're going to need a bunch of supporting functions, as in the list here, and we'll touch on a few of those. But we're mostly going to focus on the core functions because we have all of 30 minutes. The first function we're going to talk about is precision motion, near and dear to our hearts because we're XY stage people. And the simplest thing to start with is that the samples, and this is just an example, it could be a flow cell, it could be a microtiter plate, it could be a slide array. The samples are larger than the fields of view, and therefore you have to have XY motion to tile the whole image. Global flatness of the motion, but most importantly of your sample, is going to be larger than the depth of field, especially for high numerical apertures, and as a result, you need to focus. And then it is possible that not the global flatness, but the local flatness, just within your field of view, may be a little off. And in that case, we may need to add a tip tilt function so as to make the plane of the field of view, each field of view, normal to the optical axis. And then we're going to be talking about 3 imaging modes today. The first is sequential field imaging, and that's basically where we move very quickly to a new field of view, stop, and acquire an image. Another one is TDI scanning imaging, where we're moving at constant velocity and downloading the image continuously. And the third is volumetric imaging, where we are looking at a thick sample and looking at it in 3 dimensions and taking a lot more data. We'll be talking about each of those. For all 3 of those modes, the highest performance by far occurs when you use linear motors. We offer both screws and linear motors, but we dominantly focus on linear motors. This is direct drive and offers dramatic performance benefits over friction screws, ball screws, and or piezo. Now, here's a quick rundown of the Dover Motion Smart Stage ecosystem. We have Smart Stage XY, Smart Stage Open Frame, Smart Stage Wedge Z, and our award-winning DOF5 focus stage. And a characteristic of these axes, these stages, is that the complete servo driving control, which for some folks, that's a 19-inch rack mount affair, they are all condensed into these stages themselves. The cross-section of the Smart Stage is 25 high by 90 wide. It's got a lot of things in there, but it also has a very high performance driving control. And so all you do is provide communications and DC bus, and you're off to the races, and you can do multiple axes chained as nodes on a network. It makes your entire instrument a lot smaller. It's actually more cost effective, but we have cut no corners. In fact, we are achieving the highest performance levels everywhere, anywhere with this system. So I mentioned sequential field imaging. There's basically 2 things you have to do. You have to move really fast, and then you have to hold really still. And that's then you turn on the lights, that's the red. You do the illumination, you integrate the photoelectrons, and then lights out, and under the cover of darkness, you charge on to the next field of view and simultaneously download the image. And there's a bit of a tug of war here between who's the long pole in that tent. And I have to say that up until recently, it was like, you need a faster camera. Unfortunately, the cameras, and we'll talk about these, have gotten so fast that we're back to being the long pole in the tent. But we're very good at it, but still, it's never fun being the long pole. To really maximize throughput, you need to turn up the light intensity, very high fluence levels, you need to have very high speed motion, and you need to have a fast camera. Now, it turns out that linear motors are very powerful, but they also have a weakness. Weakness is because when you're doing high resolution microscopy, you have to vibration isolate the instrument from the surrounding environment. There could be somebody elsewhere on hopefully the next bench, maybe even your bench, who's vortexing or centrifuging. You can't image crisply with that unless you do a very good job of vibration isolation. And we're going to be showing you what we've done, and is in 2 booths at the show today, extremely good vibration isolation. However, the combination of a linear motor and vibration isolation is really a double-edged sword. And this only occurs to people once they're kind of deep into their project, and it has really serious repercussions. What happens is we make the very fast move. The harder we hit that, the higher the inertial forces, and those inertial forces go into the vibration isolation system, and especially if it's some crude rubber bumpers down at the bottom of the instrument, the whole thing becomes a bouncy castle, and the settling has to wait until that all rings out. Things do better if you go to more advanced isolation, but it's still a problem. That low frequency, crude isolators actually have gain at low frequencies. It's even worse. It's a resonance. But as it happens, we have solved this problem. Our advanced technology, repetitive motion enhancement, although it also works for single moves, drives the settling time literally to 0. And I'll show you that in a moment. And depending upon a choice we make, the following error during multiple G acceleration can stay within the settling criteria during the entire move. So here's a 2mm move that's done at fairly modest acceleration. I think this is half a G. And we're plotting the following error versus time. Now, in this case, we intentionally allowed, normally there's a bipolar following error. During accel, it's of one sign. During decel, it's of the other. And then you have to wait for it to settle out. Well, in this case, we've allowed the acceleration following error to print through. We don't have to, but we let it in this case. but there is no symmetrical peak on the other side. And we have settled within the settle window in 27 milliseconds, but you can't start imaging then because you're still moving. So once the move is actually complete, that's when you can begin taking an image. But for the entirety, from that moment on, including the entirety of the integration time, we are totally settled. So we're actually putting tiny currents into the system, we're actually controlling things, but the result is essentially zero settling times. In this case, we've turned on the functionality for both accel and decel. And in this case, the settling window is plus or minus 50 nanometers. What you're looking at here is a total of plus or minus a quarter micron. We're doing a 1.2 G move. It's 3 millimeters. We're doing 8 of them. And this is that vertical line there is the moment at which the motion, the trajectory stopped. And you'll notice that we are within the 50 nanometer settling window and we stay there. And we do that in 42 milliseconds, pretty fast. Now, the other imaging modality is TDI scanning imaging. And here's a little graphic that shows how that happens if you're not familiar with it. The stage is moving at constant velocity, and any given point on the object is falling on successively different pixels as it scans. And as a result, as the photoelectrons are summed, the signal gets brighter and brighter as it goes on. So in TDI imaging, there's no dead time where you're dark, you're imaging all the time. Now, I mentioned here that it requires extremely constant velocity motion with highly accurate triggers. So those triggers are what are used to advance, it's called a vertical transfer, on the array. And you could do those with a clock, but that's a bad idea. You do them based on position from the encoder, and it has to be very accurate. So as I said, we generate those triggers, and we do so based on position. Our stage resolution can be as fine as 305 picometers, one aluminum atom, but we can set the resolution to just about anything. To give you an example, let's say that you want the triggers to come out every 200 nanometers. And let's say that our resolution is 10 nanometers. So every 20 counts, we generate a trigger. But your granularity is coarse. You could do 19, you could do 20, you could do 21. That's a 5% error. So if the resolution is in fact set to 10 nanometers, in between 9 and 11, we offer 32,000 discrete resolutions. It's almost infinite. That was not hyperbole when I said extremely. So what you do is you lay down a chrome on glass artifact, you measure it, and you figure out what the magnification of that particular system is, and you just doodle it in, and you've got perfect triggers. So anyhow. Then there is volumetric imaging. Samples can either be thin, planar, 2D, or thick, 3D. Now, when we say thick, I don't see much that's beyond 40 or 50 microns, but thick. So when you're doing volumetric imaging, and AKA spatial biology, it's super important as we try to understand the interconnections between cells in tissue, especially brain tissue, neurons. We have multiple strategies to do that. We support traditional Z-stack imaging, where you take a picture, move in Z, take a picture, rinse and repeat. And we do that extremely well. Some numbers there. 250 nanometers in under 1 millisecond, 1,000 nanometers in 1.33. So very fast. So especially if you have a lot of light, you can generate that stack pretty quickly. I'll talk a little later in the presentation about another trick, tilted sample imaging, and also diffractive phase masks. So here's a plot of a 1,000 nanometer Z-step. And if you look at the red bit there, that's the time is 1.33 milliseconds. We're settling to 100 nanometer window. And that's laser interferometer, 10 kilohertz, that's reality. So we'll move on to our second core function, which is optics. And I'm really excited about a major advance that's been made here, not by us, by one of our partners. That partner, well, we'll get to that in a second, but traditionally, when you're designing a system, you had two choices, and they were both a little tough. One is that you buy an off-the-shelf objective and tube lens, and you can do that, but you're going to hit some compromises. You're not going to get the field size that you might want, and you're going to have, especially if you're not plan, you're going to have some fuzzy corners, you know. So there's the COTS choice, and then there's the custom choice. And the custom choice can get you just about anything you want, but the problem is going to be that you're going to have to shell out an enormous amount of money, and you're going to have to wait a very long time. Objective gestation mimics human. It's really thrilled that our partner, IDEX Health and Science, the Melas Griot former name, have recently productized a valuable third way, custom optical performance with no NRE and short lead times. And there's another player I'll mention later. They've come out with their X-Plan CCG line, which is a very wide range of NAs from 0.5 to, it isn't ready yet, but I believe there's a 1.1 numerical aperture immersion. And then a complementary line of tube lenses of differing focal lengths that support different size sensors. So if you want the largest possible field, you're going to go with the longest focal length tube lens, and that supports up to 48.4 millimeters, which includes full frame sensors and very large TDI arrays. And the third core function is sensors and cameras. The backside illuminated CMOS imaging revolution shows no signs of slowing down. Now, starting back at about 2010, 2011, we began to, it really was transitioning from CCD to CMOS, and a new line of scientific CMOS sensors and cameras came about. These tended to emphasize large pixels, 6.5 and 11 microns were typical, and that's really best suited for very high magnifications and very high numerical apertures. But as time has gone on, Sony has been developing more and more backside illuminated CMOS sensors, and they are now very close to scientific CMOS in performance, more cost effective. And just in November, two Sony sensors were announced, the IMX 925 and the 926. They're both the 2.74 micron pixels, similar to the IMX 531, 541, most of the 500 series. But what they do that is absolutely mind-boggling is frame rates, getting that information off the chip at just dramatic rates. So in the 24.6 megapixel, 19.3 millimeter diagonal sensor, that will do 442 frames per second, and the smaller 926 will do that in 588 frames per second. So this is pretty crazy. Now, you're never going to pull off those frame rates if you're doing fluorescence imaging because they're light starved. But there are certainly applications in life science and diagnostics where it's bright field and you've got all the light you need, and in that case, you can do this. And in particular, there's some applications that really depend upon that high frequency. These sensors will shortly be available. Emergent Vision Technologies, John and Michelle, are you here? Yeah. Hey, right, okay. They've got their Zenith series, which is 100 gig E, and they're at booth 2132, right? Is that right? Okay. Go talk to John and Michelle. Teledyne recently announced their Falcon 4 67 megapixel camera, 2.5 micron pixels, 29 millimeter diagonal, 90 frames a second at 10 bits. Mike, you here? Didn't make it, but anyhow, talk to Mike over at booth 327. And just last week, I'm looking at the Canon booth from here. Canon announced a monster 410 megapixel full-frame sensor. I haven't quite figured out why you would use 1.5 micron pixels with most microscopy applications, but it does do true charge summing 2x2 binning, and at that point it's a 100 megapixel and it supports 24 frames per second. Now you may think 24 frames a second, that isn't all that fast, but when you're talking about full frame, that's actually pretty huge. So then what I was just talking about were the sequential field camera technologies. We then move on to TDI sensors and cameras. And TDI line rates are now at 1 megahertz and headed higher. EVT again has their pinnacle line, 8K, 5 micron pixels in a 100 gig E download. And Teledyne actually has a 16K. Now at 5 microns, that's 80 millimeters, and IDEX isn't quite up to that yet, but with the largest focal length IDEX tube lens, and if you ROI that 16K sensor to 9,680, you're maxing it out. And at that point, at a numerical aperture of 0.5, the swath would be 2.5 millimeters in width, and you would be doing it at 260 millimeters per second, which is pretty blazing fast. That's, by the way, 150 billion bits per second. And if you go to the 1.1 numerical aperture, you get smaller pixels. You're only going at 114 millimeters a second. It's water immersion, so good luck with that. But and that's a 1.1 millimeter wide swath. Now, I mentioned earlier a couple other takes on volumetric imaging. Normally, you go to great lengths to make sure that the plane of the sample is perpendicular to your optical axis so that your corners are not out of focus. There's actually an interesting technology in which you intentionally tilt the sample, and now your focal plane passes through the sample, and so you're imaging the bottom of the sample on one side and the top of the sample on the other side. And you might think, how does that work? But you scan and take lots and lots of pictures and then use GPUs to kind of sort it all out. So you can get volumetric imaging pretty quickly doing that. And then something that I've only learned of fairly recently, and Leslie here is with, and Scott are with Double Helix Optics. They're in the Colorado booth. We'll call that out in the shout out page. But they insert proprietary diffractive phase masks in the objective or above the objective, and in doing so, in the infinity path, can take the depth of field up by a factor of 2 to 6 in what would be their volumetric mode, and up to 20x in 3D mode. In 3D mode, they do an engineered point spread function, and in the corkscrew 3D mode, a single point becomes a pair of flower petals at 180 degrees, and the angle tells you where it is in the sample, and the centroid tells you its location. And there are reconstruction computational modes to get back to the full resolution, but it basically gives you the whole thing. So what would be a 5-slice MIPS becomes one image. So less computation, less imaging, everything faster, all good. It probably weighs 2 grams, so how much could they charge for it, right? So pulling it all together, we've been working over the last months with IDEX Health and Science, Melis Griot, to design and build a modular OEM microscope. And we actually built 2 of these, and one is at the IDEX booth and one is at our booth. And we're pulling just about everything together there, which is high performance motion, high performance optics, and in the rush to the show, we actually have a fairly pedestrian camera, or rather, it was exciting a few months ago, but it's pedestrian today. And that is an IMX 541, which is a 17 millimeter diagonal, 2.7 micron pixels, and it's a 20 megapixel 4.5K array. It's USB 3. We're not trying to do anything blistering there because it was challenging enough just to get the whole thing imaging. But we're actually doing fluorescence imaging. We're doing it live on a display. And we're doing it with some very thoughtful vibration isolation that I barely have time to talk about, but it's pretty cool. I invite you when you're at either booth to thump on the table and look for any disturbance on the image. We've done the vibration isolation very thoughtfully, and that's working very well. I'd like to give a shout out especially to Bob Day of IDEX, who's done the lion's share of the programming of our stages and the image capture and display, and he pulled it all off in time. It's really glorious imagery. Check it out. And here's a video, if you don't make it to the booth. You can see the laser flashing away there. There's the Smart Stage XY. Some of the points we're making, and look at that imagery. Okay, now perhaps you need even higher throughput. Just, for giggles, this is a system that we did for a spatial biology company actually some years ago. It's got 4 scientific CMOS cameras and 4 objectives and 4 focus stages and 4 WDI autofocus, laser continuous tracking laser autofocuses. So pretty high throughput there. Now, on this, you can see the vibration isolation. This is our own design with help from a customer. So we've got an isolator here, and another one in the central rear, 3-point. And the one in the back is higher. So if you fit a plane through the isolators, through the top of the isolators, that plane intersects the optical axis at the sample plane. And in addition, underneath the plate that the lower axis stage is on, right behind here, there's a big, thick steel plate. And we can actually shift that front to back just to make sure that our models are reflective mass props. But the bottom line of that is that if you push on the top and the whole thing rotates, the center of mass, and therefore the center of rotation, is again the intersection of the optical axis and the sample plane. So all too often we see vibration isolation done very badly and bouncy castle, but this is quite good. And again, feel free to thump away. I'd like to do some partner shout outs. I've already mentioned IDEX Melis Griot, booth 949 with their X-Plan CCG series, high-speed aerial and TDI cameras, Emergent Vision Technologies, booth 2132, and Teledyne, booth 327. Laser autofocus, WDI, booth 1566. Diffractive phase mask, depth of field enlargement, double helix optics, booth 2332. And a longstanding customer, and I've recently learned that they've got a line of high NA, large field objectives, and that's Opticos. There's Steve over there, and they're in booth 841. So with that, whoa! How did that happen? So I'd be happy to entertain any questions.